Good day, everyone, and welcome. Thanks for joining the Cognitive Systems Institute Speaker Series call. Today, I'm happy to introduce Kevin Sullivan. He is an associate professor in computer science at the University of Virginia. His PhD in computer science is from the University of Washington, where he worked with David Notkin on software architecture and evolution. He has worked on issues including modularity and the economic value of flexibility in design, programming language features for aspect-oriented modularity, and formal methods for design space exploration. He is the founding associate editor of the New Journal of Learning Health Systems and is co-chair of a series of 3 ongoing workshops on Cybersocial learning systems sponsored by the Computing Research Association's Community Computing Consortium. Today, Kevin's going to talk to us about cybersocial learning systems, and thanks for being our presenter, Kevin. I'll turn the call over to you.
Well, Diane, thank you very much for that introduction, and good morning, everybody. It's my honor to be here. Today, I'm going to give kind of an interim report on this topic of cybersocial systems and some preliminary results coming out of this series of CCC workshops that I've been co-organizing over the last 6 months or so. My collaborator, my co-organizer of that workshop series is Chuck Friedman, chair of the Department of Learning Health Sciences at the University of Michigan. So this whole initiative came out of Chuck and my earlier collaboration on what we called learning health systems. That's a construct framed by the Institute of Medicine, now the National Academy of Medicine, and their deliberations are recorded in a long series of workshop reports out of the IOM. A challenge that I faced in trying to work on this topic of learning health systems, health delivery systems that reflect on their own performance, derive new knowledge from data, and subsequently improve their practice and performance. A problem that I had working in this space is essentially a kind of a lack of foundation support for the involvement of computer scientists in healthcare delivery systems. There's some modest support out of one program in the NSF, but really there's not adequate support to bring the computer science community in a very substantial way to bear on problems of the construction and evolution, the realization of this vision of a learning health system at a national scale. So Chuck and I went to the National Science Foundation, had a long conversation with them, and came out with the view that there was a larger issue of learning cybersocial systems in general. These are, in particular, service delivery systems for healthcare, education, transportation, defense, you name it. And it was our view coming out of that meeting that all of these systems could benefit enormously from the introduction of this concept of kind of self-monitoring, self-analysis, planning and implementation of improvements based on knowledge derived from data, thereby turning these systems into learning health systems. So that's sort of the background for this. The NSF encouraged Chuck and me to go to the Computing Community Consortium, a standing committee of the Computing Research Association, whose mission it is to encourage the community to engage in visioning activities to help define the future of computing research. And so that's what this is really all about. And the idea is that the outcomes of this workshop series, which just finished last week, will help to inform and advise policymakers in the National Science Foundation and other agencies regarding future opportunities for research. So that's where all of this began. So let me advance to the first slide here. The framing that we used for this workshop series was as follows. We've made enormous progress on scientific and engineering principles for cyber-physical systems as distinct from cyber-social systems. Cyber-physical systems essentially combine control theory and sensors with computing and actuators to enable highly novel functionality and improved performance in many kinds of physical systems. The Work that's been done in this area is leading us into an Internet of Things, a world of physical systems that are computational and connected at all scales. And we're seeing just amazing improvements in system function and performance, things that we've never seen before, coordinated swarms of drones, for example. The cyber-physical systems community is at an interesting point, however. It's beginning to have to look at the integration of cyber-physical systems with very complex human and social organizational systems and phenomena. And it's our view that the theoretical foundations, if you will, of the cyber-physical systems community, rooted in the integration, again, of control theory and discrete computing, really not up to the task of providing adequate principles and foundations to guide the integration of all of this technology into complex human and social systems, such as healthcare delivery systems, education systems, community service systems, national defense systems, and so on and so forth. So we envision a new class of systems, or to newly recognize a class of emerging systems that we're calling cybersocial learning systems. These are systems that leverage cyber-physical systems technology, AI, machine learning, software engineering frameworks, the whole gamut of computer science and systems engineering capabilities to produce socio-technical systems that are high functioning and continually improving. So you see a list here of the many domains in which we think these ideas will play out. And the particular focus of this CCC workshop series was on essentially the design and operation of cyber-social service systems, service delivery systems for healthcare services, for example, with quite audacious goals. So, many of you probably know that it's estimated that between 100 and 400,000 people die each year due to avoidable medical errors in the United States alone. How can we reduce that by 90% within 20 years? How can we truly achieve grand challenge problems in education, such as getting most children reading at grade level in the 3rd grade? How can we provide radical transparency into the operation of cities and communities and all of the services that they provide? So this is the overall framing of this effort. Now, my outline, sorry, I'm somehow missing a couple of bullets here, but the outline of this talk is as follows, and I'm going to have to move along pretty quickly. First, I'm going to try to distinguish socio-technical, cyber-physical, and cyber-social systems to give you a framing for that latter term. Next, I'll talk about some of the key elements of cyber-social systems. And finally, I'll just go through some of the emerging ideas that have come out of this series of workshops. And these are ideas contributed by participants in these workshops. So let me start with the first bullet. I want to distinguish socio-technical, cyber-physical, and cyber-social systems. Socio-technical systems, it's a topic that's been studied for decades. These are viewed as systems comprising people, machines, computing, physical elements. There's a picture on the slide here of an air traffic control system, for example. And there are many service systems of this kind. Key points are that these systems often are not designed for rapid and comprehensive and dramatic learning. We often see a glacial pace of system improvement in these systems, and that's true in air traffic control, in healthcare, in education, and in many of these systems. It's not that they don't learn at all. They do, of course, for example, from accident analyses, but the systems overall are designed for very limited rates of learning, and the emphasis is often on performance and reliability as opposed to rapid evolution toward higher states of fitness. So let me talk quickly about human-in-the-loop cyber-physical systems. The central objective of much of this work is to optimize the functionality and performance of physical devices as opposed to complex human-intensive socio-technical systems. All of this work in CPS, as I said, is enabled by advances in sensing and the integration of discrete computing through a kind of integration of control theory and logic, leading to models such as hybrid automata. These systems increasingly use machine learning And now we're seeing the integration of discrete logic and probability theory to enable cyber-physical systems to deal with uncertain environments. These systems often involve humans in the loop to handle control, for example, when the machines are unable to do so. But the tendency in this space is to progressively reduce the human role in these systems to the extent that's possible. And so, examples are abound. So, for example, here's a picture of basically a human-free cyber-physical system. This is part of a Mercedes-Benz manufacturing line, and the robotics here clearly have all kinds of sensors and actuators, and they're going about doing their job of putting cars together. This technology has enabled pretty amazing advances. Here's a gentleman, Mr. Brown, sitting in his Tesla, which, as everybody knows, is now capable of substantial levels of automated driving. The Tesla system as a kind of distributed or decentralized cyber-physical system is really quite incredible. Every car employs machine-learned models, among other things, to implement fast local control for obstacle avoidance, lane centering, and these sorts of functionalities. Moreover, every one of these vehicles is interneted to the Tesla cloud, which has collected upwards of 1 billion miles of driving data so far, much of it while Tesla's autopilot functionalities are engaged. Machine learning and other forms of learning are implemented in the cloud, and then updates to the control systems are downloaded back into the vehicles to improve their functionality. So in some sense, this is a learning, in a clear sense, this is a learning cyber-physical system, and it's quite impressive in what it has achieved. Here, for example, is a little bit of a kind of a cartoonish graph that shows in gray human lane centering performance, and in red lane centering performance when autopilot is engaged. Clearly, the car is doing a better job lane centering. Strangely enough, you see in the human lane centering a sort of bias to the right, and maybe the machine needs to learn that safety is improved by moving a little bit outside of the center of the lane, but that's a policy issue that could easily be implemented. More impressive is this chart here. It shows, this is a chart from the very recently released accident analysis report in the wake of a crash of a Tesla that many of you have heard about. This data collected by Tesla shows that when auto steering is engaged as part of the overall autopilot functionality, the crash rate per million miles is reduced by 40%. That's a remarkable achievement. At the same time, these systems are still prone to failure modes, and in particular to new kinds of failure modes. So here's Mr. Brown's Tesla. After a truck crossed in front of Mr. Brown's path, he was watching a movie. The car went under the truck, and the top of the car was sheared off, and Mr. Brown lost his life. A little diagram of what happened in this case. So what we see here is a cyber-physical system that works great, except when it comes to the interaction of kind of the human component in the system. There was an issue of Mr. Brown's trust in the Tesla's autopilot functionality versus its trustworthiness relative to his expectations, and there was a real mismatch there. Mr. Brown clearly was over-trusting the technology relative to its actual and even documented capabilities. Just the last bullet I want to kind of point out, a second less widely recognized failure mode in this case is that car continued driving even after it passed under the truck. It didn't stop until it hit a telephone pole. So it's not as if the trustworthiness of cyber-physical systems is a resolved issue. But what we see here is that as cyber-physical systems technologies begin to interact with human beings, we have to deal with whole new sets of phenomena. The CPS community is sort of inching up to and being forced to deal with CPS-human integration, but its principles are not adequately developed to deal with that at a high level. So in some sense, we want to move, the concept of cybersocial systems takes us from this primarily cyber-physical system, albeit with human in the loops, to notions of very large-scale cybersocial systems. So here's a similar picture from Chuck Friedman of a kind of a graphic of a learning health system at national scale. And what you see here is the idea that the nodes in this graph are now key elements of healthcare delivery and research systems, research institutes, public health agencies, community practices, federal agencies, health centers. And the idea now, of course, is that these systems are going to be learning, they're going to be communicating with other analytic capabilities and new knowledge and functionality and so on and so forth will be delivered back out to the edges of these systems, resulting in substantial improvements in functionality and performance. So the idea then is that cybersocial learning systems seek not just to improve the performance of physical devices, but of human-intensive systems, service delivery systems, enabled by advances and the integration of at least 4 forms of thinking: computational thinking, systems thinking, design thinking, and social thinking. And that social thinking element is absolutely crucial. We're talking about thinking in terms of everything from cognitive psychology to mechanism design to behavioral economics and beyond. This will enable us to move from sort of unprincipled and ad hoc integration of computing technologies and human systems to a much more effective basis. So I want to just give you 2 kind of graphics here to communicate different views of a cybersocial system. This is a chart by Ben Schneiderman. In the green at the bottom, you have the people and the delivery systems that you're trying to improve: patients, customers, passengers, students. Above, you have the people who are essentially kind of monitoring and analyzing and trying to deliver improvements into that system. To the left, you have regulatory agencies and forms of independent oversight. And of course, these systems are often threatened by malicious actors. Oh gosh, I see that this slide has not rendered well on the display here. Let me just bring it up on my own computer here, and I will talk through it. Quickly.
You'll have to stop sharing the file and share your screen.
That's okay. I think let's see. I don't actually have this up on my screen. I have it up on my laptop. So let me. I can take you through it. So this is a highly simplified kind of schematic of some of the key elements of what we consider a cybersocial learning system. So in the light yellow box at the bottom, I've depicted a socio-technical system. This is the system that's meant to be improved by cybersocial learning systems approaches. And all of the words that you can't see under that big socio-technical system label are characteristics of the kinds of systems that to which we want to apply cybersocial systems approaches. And they're decidedly not the same elements that you see in physical systems. So these socio-technical systems do live in physical environments. They have artifacts, tools, and resources, but they're also intensively populated by people, institutions, services, workflows, and various performance characteristics. They rely heavily on tacit knowledge embedded in individuals, organizations, and large systems. They incorporate human values, competition, economics, incentives, goals, politics, and power. One always faces human quirks such as irrationality, bias, intentionality, agency, again, power, belief systems, cognitions, and again, quirks of human behavior. People in these systems hold values. They have norms, culture, laws, policy, regulations, and pressure to behave in certain ways. These systems include oversight, governance bodies, allocation of responsibilities, authority, distribution of resources, accountability issues, enforcement mechanisms. And of course, they have feedback loops and system dynamics of various kinds. So that's the kind of target system that we're talking about. Those are the kind of key elements of a healthcare delivery system, for example. Now, in the blue font at the bottom and in the blue box at the top, these are the additional elements that we see as being, or some of the additional elements we see as being necessary if you want to turn a socio-technical system into a cybersocial learning system. So in blue typeface at the bottom, we imagine that these systems are now cut through with cyber-physical infrastructure, various kinds of sensing modalities, processing, collection of data, lots of software, AI analytics, autonomy, and of course, logic of control. These systems also would include such things as human sensing mechanisms, communication infrastructures, large-scale group coordination, negotiation mechanisms, incentives to align human actions with overall system objectives, and this sort of thing. So at one level, turning a socio-technical system into a cybersocial learning system involves the incorporation of all of this kind of advanced computing stuff, much of it human-centered, into these systems. But to have a learning system, you also need a control loop, a learning loop, and that's what's depicted in the blue box at the top. So there's sensing of what's going on in the cyber-technical system, enabled by all that technology. There's analytics, planning, and the design of interventions off on the right lower part of the blue box, the design of interventions into socio-technical systems to move them in directions that are more consistent with overall learning and system improvement objectives. At the center of the control system box, the blue box, if you will, but let's not call it a control system because you can't control socio-technical systems, you can only influence them. So the blue box is maybe an influence theory box rather than a control theory box. Nevertheless, at the center is a set of models based on observations and data, leading to theories and hypotheses, along with evidence and judgments about their validity, where these system models are about the control system itself, the socio-technical system being managed, and the environment in which it lives. And so the idea here, of course, is that you really analyze what's going on in your healthcare delivery system. You learn new models from advanced analytics. For example, maybe you can tell when healthcare delivery personnel are too fatigued or stressed out to be able to work safely. And at that point, you can intervene in the system in a way that is informed by social science, organizational theory, ethics, and so on and so forth to reduce the likelihood of an accident. So that's an overall kind of highly simplified diagram of what's going on. Of course, there would be many such control loops in such a system. The system itself would have lots of structure, and so it's more complicated than that. The real problem is that today, the practice of building such systems, to the extent that they are being built, outstrips the scientific engineering and design foundations. We really don't have a discipline today of cybersocial systems. We want to move beyond just descriptive and predictive theories of, computer-intensive socio-technical systems to a framework where we have valid bases for prescriptive and interventionist design of such systems. We want to have the actuators, if you will, properly designed in light of the fact that what they're dealing with is a highly complex human system. We're looking to develop principles, methods, and technologies for cybersocial learning systems understanding and development, with impact seen in major improvements in many critical societal systems over time. So in this workshop series, we asked what are the gaps in knowledge today? What approaches might we develop to deal with these gaps? How would we evaluate the impact of improvements in cybersocial systems, fundamental knowledge and technologies? And how would a research initiative address uncertainties, risks in such a program, and the problem of getting to scale? So I'm going to spend just the last minute of talking by surveying very quickly a couple of interesting research topics of interest that bubbled up out of this workshop. How do we build motivational structures for technology-mediated social participation in a cybersocial learning system? What are the mechanisms for large-scale coordination of complex human tasks? How do we deal with quality and analysis of data from online social networks and sources? A lot of socially acquired data is not IID, and so conflicts with basic assumptions in the machine learning community today. How can we think of humans as sensors? What about social media exploitation tools? We need greatly elaborated theories of learning to underpin a theory of human organizational and systems learning in CSLS. We need principles for integrating human and AI robotic elements of systems, the organization of computable knowledge at scale for decision support at scale, person in and on the loop system design, ethical, regulatory, and legal aspects, design and measurement, control, and assurance of critical system properties, designing these systems for ease of observation, experimentation, and adaptation. This is highly multidisciplinary work, and we lack the foundations for multidisciplinary model integration. And we need to understand how the dynamics of public opinion serve as an enabler or disabler of action based on knowledge in such systems. So we ran this series of workshops, and that's sort of where we've gotten to. I'm out of time, and so thank you, and I'm open for questions.
Thank you, Kevin. That was great. So relevant and so interesting. Audience, please press *1 on your phone to ask a question or unmute your microphone on your computer.
Hey, Kevin, this is Jim Sporer. Thanks for presenting, and it was great to be part of that Cybersocial learning meeting that you had up in Washington, D.C. Could you summarize, I know you've had the series of workshops now, can you summarize where it kind of stands inside National Science Foundation or other funding agencies or any foundations stepping up to fund some of this work?
Well, Jim, thank you for that question, and thank you for being involved. We certainly appreciated your input and your thoughts on both service systems and cognitive systems technologies. This CSLS concept clearly sits in a context that is deeply informed by the thinking that you and your colleagues have done in both of those areas. We just finished the third and last of the workshops last week. We're in the process now of formulating our overall outcomes, recommendations, and corresponding reports and slide decks. So we haven't yet gone to the foundation. You know, we have been in communication, of course, with people at the foundation and elsewhere, but at this point, you know, we haven't made an ask, as it were, and so it's still a little bit early to think that there would be any action on the part of the policymakers at this point. We're just not quite there yet.
Okay, and I'm going to send you an invitation to an NSF-sponsored workshop that I'm co-PI on that's out here in Silicon Valley, March 29th and 30th, and you know, it would be great to get some of the cyber-social learning system thinking that you've developed and presented here into that workshop. I think it would inform and align really well. It's a smart service system workshop. So thanks again, Kevin. I'll send that to you.
Yes,
right away.
indeed. Thank you very much. Yep.
Thanks, Jim. We have about 1 minute. Is there anyone else who has a question? Scott, I'll forward your question to Kevin after the meeting. Anyone else have questions? All right, we're just about out of time, but I'll ask a real quick one. And Kevin, is cybersocial systems being taught in universities?
Oh, that's a great question. Not yet, not as a discipline. I mean, this has really a rapidly emerging area, but it's still been emerging pretty much in the group of people who have been involved in these workshops. The idea that we should formulate a curriculum for, if nothing else, than for a graduate seminar or a class or two is definitely on our agenda. The production of bibliographies of work related to this topic from Klein's work on multidisciplinary investigation to service systems and cognitive systems, all would be relevant. But no, we haven't gotten there yet either. So this is a very early peek. This is a very early peek at what's coming.
Yep, it'll be fascinating to start the studies on that. Well, thank you so much for being our presenter. I loved your presentation. Audience, thank you for joining. We have another great speaker next week, so please come back. And thanks again, Kevin. We'll see you next time.
Diane, it's been my pleasure, and thank you to everyone who was on the call. I really appreciate it. Happy to take questions and comments. My email address is on the screen.
And we'll also continue the conversation on our LinkedIn discussion group. Thanks, everyone.
Terrific. See you there. Bye-bye.